Turned it on already.
I did, yeah. Give it a tap just to make sure. Yeah. You ready to go?
Oh, yeah, I'm ready.
All right, let's get started. So we are glad to have Tom back telling us a little more about this morning, Rindler positivity.
Okay, so last time at the end, we started talking about this other positivity. So at the beginning last time, we talked about reflection positivity. That's an ordinary positivity in Euclidean, where correlators are positive when they're reflection symmetric, because that can be interpreted as a norm. And then at the end, we started talking about this other type of positivity, Rindler positivity, which it follows reflection positivity, but in a pretty non-trivial way, and is important for the structure of Lorentzian correlation functions. So I'm going to prove this, but I first want to give a sort of intuitive reason for it, which I won't try to make this intuitive one precise. We'll prove it a different way. But let me see. This is okay. So you're going to have to stop me if this doesn't make sense, because we're going to have to analytically continue out of the board, and I know what's happening in my head when we do that is not always the same as what's happening in your head. Okay, so let me start with the case where we just have the two operators inserted. Okay, so we have one on each side. Now, this is positive by reflection positivity, but it's not it's not quite the same reflection positivity we discussed last time, because that was reflection in Euclidean time. But if we imagine taking Euclidean time and imagine the direction out of the board is Euclidean time, and so Euclidean time goes that way. Now the reflection in Euclidean time would be like out here in there, right? But in Euclidean time, you can any which way. And I could have said that this is Euclidean time. On the Euclidean picture, I'm perfectly allowed to say that that was Euclidean time. And this kinematics, where you have these two operators, one on each side of the Rindler wedge, that actually is reflection symmetric with this other type of Euclidean time, with the other Euclidean time. Yeah.
Just to be sure, this plane is like just because it's a three-dimensional space-time, it's not because you went into a complex plane, or it is a complex plane?
Right. It's a complex plane. It's not the transverse like spatial directions. This is the complex plane.
Like complex direction of a space-like coordinate?
This is the complex. Let's suppose for a minute the theory is two-dimensional.
Yes.
And so this was the t direction, and this is the usual tau equals it direction.
Oh, good.
But you could draw the same picture in higher dimensions. Same stuff applies.
But the horizontal line goes through. Isn't that the x-coordinate then? Or in this picture?
This line?
No, the other line.
This line. Yeah, it's the x-coordinate, but the important thing is that it's also the line tau equals 0, and you can reflect around it in Euclidean signature.
Okay, yeah.
This line is the weird line.
Yeah.
So that line is only there when you go to Euclidean. It's not anywhere in the Lorentzian spacetime.
Thank you.
Are we so far so good? Why this 2-point function had to be positive? I mean, basically because we could rotate it, and then it would be a reflection positive. But I want to keep it. I don't want to rotate it. Okay, we good? Other questions? Yeah.
So it's just that like the t is out there and there's an orthogonal plane, and you can put iota t anywhere.
You could put what? Say it again.
It anywhere, which is your tau, and hence you can.
We could pick a.
Just rotate it anywhere.
That's right. When I use this line, I'm treating one of the space directions as Euclidean time. Exactly. Okay. Now we could add more points. Okay, so say we add points like this. Still reflection positive, we still have positivity. But now what I'm going to do is take those points and evolve them by e to the IHT. When you evolve those points by e to the IHT, that pushes that point into real time. And then now if you take the reflection conjugate, you also have to take a complex conjugate. So if you evolve this one backwards in time, you have to evolve that one forwards in time. So in fact, this Rindler reflection symmetric configuration that we started with is a reflection symmetric type reflection positive configuration in the other interpretation where we think of Euclidean time as that other slice. Yeah.
Could we also have done something like define the slice that goes through 2 bar and 2 as t equals 0, and then define the complex time with respect to that? Because you can.
Yeah, and then we'd have to boost the 1 operator. Yeah, we could have done that.
Sorry, just to be clear that I'm understanding the picture, you're imagining rotating the entire.
Stand. The barred coordinates are defined by reflecting doing the Rindler reflection, where you reflect. So let me write up that definition. That's the definition of bar. Okay, if this picture wasn't helpful, then that's okay, but I don't want to get stuck on it, so let's go to the other derivation, and you can ask me about this picture later if you want. Okay, so there are many different ways of deriving this positivity condition, but I think my favorite, and one that's very instructive, is by recasting this as a statement about thermal physics. So the Minkowski vacuum decomposes into, or if we decompose the Minkowski vacuum into Rindler states, the Minkowski vacuum is the Rindler thermofield double. So this 0 is our Minkowski vacuum. This I'm going to write as a sum over states n e to the minus beta en over 2 of n star L and R, where this is re-expressing the Minkowski vacuum in terms of Rindler states. So these are states in the right Rindler wedge. These are states in the left Rindler wedge. The Rindler temperature is 2 pi. Inverse temperature is 2 pi, but I just put a beta there. The star is the CRT conjugate. So J n star L m R is m star L n R. Okay, so this is the well-known fact that Minkowski space is thermal state in Rindler space. And this state here is an entangled state. It's called the thermofield double. It's an entangled state of the states on the left Rindler wedge and the states in the right Rindler wedge. And any calculation that we do in Minkowski space in vacuum has to agree with some calculation that we could do in Rindler. If I were to trace out one of the halves of Rindler space, say the left half, this is a pure state in 2 copies of Rindler space. But if I were to trace out, say, the left half here, then I would have a thermal state on, the reduced state would be a thermal state on the right Rindler wedge. Now, let's take an operator A, which is some product of local operators. It doesn't need to be a product of local operators, but we might as well. O1 of x1 to On of xn with all of these points on the right. I think I forgot to label right. Okay, so this is R, and this is L, our left and right Rindler wedges. Then this positivity condition that we're after form A bar A being positive. So I'm going to now calculate A bar A. And I'm going to do this calculation by expressing it in terms of, by rewriting it in Rindler language. So if we take that Minkowski vacuum and expand it out in Rindler states, there's a double sum over m and n, e to the minus beta, em plus en over 2. Now, A bar has, so A has support only in the right Rindler wedge. It's an operator on the right Rindler wedge. A bar has support only in the left Rindler wedge. So when we express this in terms of Rindler states, we can just pull things through and have this one acting on the left Rindler and this one acting on the right Rindler. So this is M star on the left, A bar, N star on the left, and then R, M, A, N, R. All I've done is to plug in the Rindler expression, thermal field double expression for the Minkowski vacuum. Now, this thing here, so these two things are actually complex conjugates of each other. It takes a little bit of thinking to show that. So if one way to do this is using the definition of the reflection in terms of our anti-unitary operator J, so we can write this as M star J, A, J, N star. J, so A bar is defined by conjugating with the wedge reflection. But now J is an anti-unitary operator. So this we can write as N, A, M. So now we have these two things are conjugates of each other, and we can write this as the sum over m and n, e to the minus beta, em plus en over 2 times the absolute value of m, a, n mod squared acting on the right.
All right, Tom.
Yeah.
Be a bit more explicit about how the JAJ sandwich between M star and N star turns into that, because the action you defined for J was on these two states upstairs.
Yes, let's see. Let me leave it as an exercise. It's nothing hard. It's anti-unitary. We just have to write them out. I'll mess it up if I try to. It's just one line, but I don't want to mess it up. So. Other questions? Okay, so we've succeeded. Now, this is manifestly positive. And that's what we want to show. So by expressing this in terms of its Rindler decomposition, we found a manifestly positive expression. An important application of this is called or instance of this really, is called the double discontinuity. So the double discontinuity refers usually to a 4-point function. So let's write our 4-point function g of x1 to xn is O of x1, or sorry, we're 4-point function, x4. So O of x1, O of x2, O of x3, O of x4. Then the double discontinuity, or d-disc, of the correlation function g, let's put the arguments in there, in the kinematics that are reflection symmetric, so x1, x2, x1 bar, x2 bar. The double discontinuity is defined to be 1/2 of the commutator O of x2 bar O of x1 bar and its reflection. So O of x2 O of x1. So this operator on the right we can think of as our operator A, and then this commutator is our operator A bar on the right, on the left Rindler wedge. So this is just a special case of what we've been discussing, and therefore this is positive. It's important how these things are ordered. So remember that when we do the wedge reflection, everything stays in the same order. So like O2, this is unlike what happens with an ordinary Hermitian conjugation. The ordinary Hermitian conjugation, you flip the order of things. With wedge reflection, you keep the order. Okay, and so we have O2, O1 with the bars and O2, O1 without the bars. So the importance of this is that, well, first of all, the name. Okay, so why is it named the double discontinuity? So remember the discussion last time that commutators are, so different operator orderings correspond to going around branch cuts. So commutators, the commutator is the discontinuity across a cut. And so a double commutator, you have to take a discontinuity, and then you have to take a discontinuity again. So that's the double discontinuity. That's the terminology here. And you would calculate this by taking the discontinuity across one cut, finding you still have a branch cut, and then taking the second discontinuity. So the importance of this object is that the double discontinuity plays a role in position space that's similar to the scattering amplitude, to the cross-section in momentum space. So you've probably seen some dispersion relations in, for scattering amplitudes, either in this summer school or elsewhere, where you express things in terms of the imaginary part, of the amplitude, which is related to the cross-section. And so that positive, so that gives you some rules in dispersion relations in terms of something that's positive. And the situation for position space correlators is similar, with the d-disk playing the role of the imaginary part of the forward amplitude in a scattering amplitude. Yeah?
One can in principle also introduce a dagger A and call that double discontinuity. I'm just curious about their relation.
You want to put A dagger A here?
Yeah, A is the commutator.
Or you want to put A dagger instead of A bar?
Right. Are they related to each other or just independent objects?
Well, if we literally tried to do that, this would be infinity. Okay, because so these are points in Minkowski space, and if you dagger a point in Minkowski space, nothing happens to it. So what dagger does is it reflects the imaginary part of time. It reflects you across Euclidean time, which means that in Minkowski space, like if say we have a scalar operator phi of x, a real scalar operator, then its dagger is equal to itself, and you can't insert this twice in a correlator, you get infinity.
So this definition avoids that, right? Considering its image in the other patch.
Yeah, Yeah, that's right. That's right. Yeah.
Do the points in one Rindler wedge know about the branch cuts of the others?
No, because of causality. Good. The question is whether the points in one Rindler wedge know about the branch cuts coming from the other points. And they don't, because everything over here is always space-like separated from everything over there.
But in theory, the branch cuts can be arbitrary, right?
Yeah, this is another one of these wacky windings that we mentioned a few times last time, which is that, yeah, there's a branch cut coming out, and you could wake up one morning and decide you want to go up here and walk around the branch cut and come back down over to Rindler space over there. That's a thing you can do mathematically, but it's not one of the correlators. It's not a correlator of local operators that we usually talk about in quantum field theory.
Could you explain again what was the significance in terms of position space? Like how was this related to the momentum space?
It's not that it's related. They're not equal or anything. I was making an analogy. So when we talk about dispersion relations and scattering amplitudes, a very important thing is the imaginary part of the forward amplitude. And this is an analogous thing that shows up in position space in things that are like dispersion relations and sum rules. And this is a positive thing that shows up in those sum rules. It's just an analogy, and we'll see some more of that later.
Question?
Yeah.
Would this have worked for any other anti-unitary operator instead of J, or are there conditions like it has to commute with the Hamiltonian? Is that another example?
The question is whether there are other choices of J where this would work.
Or other anti-unitary operators?
Yeah. Well, I'm not aware of any, I don't know off the top of my head whether there's anything like that other than the obvious ones you get by like choosing a different Rindler slicing, but I don't know. So I want to compare this to the time-ordered correlator. So time-ordered correlator of, I'll just write this as O2 bar, O1 bar, O2, O1. The time-ordered correlator, if we look back at the way everything is ordered here, so the time-ordered correlator is 2 bar, 1 bar, 1, 2, right? O2 bar, O1 bar, O1, O2. So this is not the one we've been talking about by swapping some of the operators. So this is not the one that's positive. And if you go back through our expressing everything in, sorry, it's not this one. It's not this one that gave us the positive expression in Rindler space. But if we take this time ordering and we go back through this argument where we decomposed everything into Rindler, what that's going to do is it's going to flip, it's going to conjugate this expression. It's going to conjugate this one. So if we go back through that, we're going to get the sum over m and n, e to the minus beta em plus en over 2 times the same thing, but without the absolute value. So M O1 O N R squared. Okay, so it's the same expression we would have gotten from the other ordering, except no absolute value anymore, which means that they differ by sticking in a bunch of phases into the sum. If we had done the other ordering, we'd have an absolute value. This has a bunch of phases. Now, this expression, or this ordering, well, first of all, this means that the magnitude of this is always bounded above by the one that was positive. O2 bar, O1 bar, O2, O1. And so this object, yeah.
Do the O's have to be Hermitian for this to go through?
No, I don't think I used that. Did I use that somewhere?
Like, because like when you use the answer unitarity, right, then you flip in an M, right? Or
No, that was all built into using J and everything. These O's don't have to be Hermitian because this bar will also put in the dagger if you have a operator that's not Hermitian.
right. Okay, I'll work out myself now.
Okay. So we interpret this in the language of thermal physics. Again, everything we do in Minkowski, you can interpret as some statement about thermal state in Rindler space. And this time-ordered correlator, this is a very important object in thermal physics. Using this Rindler thermal state interpretation, the time-ordered correlator, T of, I'll just write dot, 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 this time-ordered correlator is what's called the thermal OTOC. For out of time order correlator. In other words, if we just forget that we were studying Minkowski space and just think of this as a thermal system defined on Rindler space, this is the thermal OTOC. Now, it always feels a little backward because it's the time one, it's the time-ordered one, that's the out-of-time-ordered correlator. The reason for that is that in Rindler language, so Rindler time runs backward. Rindler time runs up on the right, and it runs backward on the left. So what's time-ordered in Minkowski is out-of-time-ordered from the point of view of Rindler time. So this time-ordered Minkowski correlator is the Rindler thermal OTOC. The reason that these thermal OTOC, so usually when people discuss thermal OTOCs, they're interested in like ordinary thermal states, not this Rindler not this Rindler thermal state that's secretly the vacuum. But there are many similarities because we can interpret the Minkowski correlators as thermal correlators. The reason that they're so important in thermal physics is because the OTOCs are a way of understanding chaos in quantum mechanical systems. I'm not going to get into that, but I'll just very sketchily say what's going on there. When we took this time-ordered correlator thermal OTOC and we expressed it in terms of this sum, this is a sum with a bunch of phases in it. So if you do this in time, if you do this at early times, if you think about this, if you do this at early times, then it'll just be some number, say order 1. But if you evolve it in time, you'll have a sum with a bunch of random phases in it, and those will tend to cancel out. So this thermal OTOC will tend to decay. So the phases in the sum cause this thermal OTOC to decay in time. And the way in which it decays is a signature of quantum chaos. So when it starts to be, then you can understand that as Lyapunov behavior and a signature of chaos in the thermal correlation function. So again, I'm not going to really get into that, but this is a topic that is really interesting. There's lots of great work on understanding the OTOCs, both in quantum mechanical systems, things like SYK, in holographic systems, and a lot of the techniques that have been developed there. So, for example, there's a famous result called the bound on chaos of Maldacena, Schenker, and Stanford. So the bound on chaos tells you about how these thermal OTOCs are allowed to behave. But you could take the bound on chaos, which is originally designed for thermal states, you can apply it to Rindler, and then the bound on chaos actually tells you something about 4-point functions in the Minkowski vacuum. So indeed, there's this correspondence, and you can borrow the techniques and bring them from one subject to the other. Okay. But I think that's all I'm going to say about the thermal correlators. But is there a question? Yeah.
It's not very related. Just when you first give the introduction of the derived Rindler positivity from reflection positivity, from the reflection positivity, would you have written just the ordering as just 020, 101, 002? When you have the reflection positivity?
If we were doing ordinary reflections, like with the ordinary dagger, then yes. But when you do the reflection across that other plane, you end up with the ordering that's positive in this way.
Oh, I see. So that is also consistent.
Yeah.
So you said people were borrowing tools from like quantum simpler than just calculating correlators?
Could you repeat the question?
Yeah, the question is like I made to rephrase a little bit. Thermal physics sounds hard. Why not just work in Minkowski? How does that help? Well, maybe I don't have a great answer to that question, but some of these things were understood first in thermal physics and only later translated into Minkowski physics. I think part of the reason for that is the intuition that you get by thinking about thermal physics and the physics of black holes, where a lot of this study of OTOCs came from. You get intuition for like how things should behave in time, what should be chaotic, et cetera. Now, in hindsight, maybe you could have done the whole thing in the other direction, but actually a lot of it came from thermal first and then to Minkowski, so I don't know. Yes?
The bound on chaos, what is the physical result in Minkowski space?
Good. So the bound on chaos in thermal language tells you how fast this is allowed to start decaying. The bound on chaos in the language of the Minkowski space correlator tells you how fast the correlator is allowed to change in a limit that I'll talk about probably. Limit where you take some of these, you take this 2 operator and you send it way down there. So you send that one way up there and this one way down there, and there's a bound on how fast the correlator can change, and that's analogous to the bound on chaos. One thing it tells you about Minkowski space quantum field theories is that they can't have isolated higher spin particles. So this is an application. If you were to have an isolated higher spin particle, it would cause the correlator to change, its Minkowski space correlator to change in a way that's not compatible with the chaos bound. Other questions? Yeah?
Just to piggyback, was that for a massive or massless particle?
For the higher spin particle, both. Yeah. Massless or, the question was massless or massive. Answer, both. Other questions? Yeah.
Is the role of the purification important here? Because in OTOX, I guess people would think of just a single thermal state rather than purification.
Good. So in OTOX, the question is it important that you purified? Because usually in thermal OTOX, you don't need to purify. There are different versions. The answer is there are different versions of the thermal OTOC. There's one version where you don't purify, and you just do everything in a mixed thermal state. But there's a very closely related thermal OTOC where you purify, and they're just related to each other by some pretty simple analytic continuation. So actually, all the physics is in both of them. Okay, let me see. I am going to change gears now. And return to the average-null energy condition. So remember, this was a statement that if you take the null-null components of the stress energy tensor and integrate them over a complete null ray, that this is a non-negative operator. So we'll come back probably next time to how it's related to what I've been talking about so far. The short version is that if you want to prove the ANEC, the ingredients that go into proving the ANEC are all the things that we talked about, like Rindler positivity and all these branch cuts, et cetera. But for now, I just want to talk about the ANEC on its own. So why the ANEC, first of all? So first of all, in any quantum field theory, it's a general fact that local operators, any local operator, including the stress energy density, stress energy tensor, or energy density is unbounded from below. Now, if we integrate it, so this is a local operator. All local operators are unbounded from below. Of course, if we integrate it to get the total energy, then that's bounded from below in a good quantum field theory. But the point is that locally, it can be very negative. And but what this is telling you is that if there's negative energy in one region of space, then there has to be even more positive energy. So you can sort of borrow some negative energy, but overall, it has to add up to something positive. And you could ask, well, you could ask, how much do you really have to smear to get a positive operator? Do you really have to calculate the total energy of the entire space in order to get something positive? Or maybe if we just took this, local operators are kind of weird in quantum field theory. They're very singular. They don't make normalizable states. Maybe we could just smear this a little bit and get something positive. But no, that doesn't work. In fact, any positive operator must first of all not create the vacuum. So that is the operator acting on the vacuum must be 0 as a state. Yes?
If I take a positive operator and I add a positive constant, should that still be a positive operator?
Yes. Does that bother you?
Wouldn't that not annihilate the vacuum anymore? Or just like be the constant times? It wouldn't be the vacuum wouldn't be a zero out of the state.
Yeah, yeah, we can always shift it. I'm going to shift it so that so its vacuum expectation value is 0. If we define things so its vacuum expectation value is 0, then it has to annihilate the vacuum. Now, this statement that annihilates the vacuum, this is a much stronger statement than its vacuum expectation value being 0. So this is very easy to prove. Let's look at some matrix elements of our putative positive operator. And I'm just going to pick 2 states. Let's look at the vacuum state and some excited state that I'll call 1. And then we'll calculate those matrix elements. OK, so we've defined our operator so that it's 0 in vacuum. Just shift it so it's 0 in vacuum. And now suppose that the other entries of this matrix are B, B, and A. Well, this matrix has a negative eigenvalue. Unless B is equal to 0. That's very easy to check. And what that means is that if B is non-zero, then you can form some linear combination of states 0 and 1 such that the expectation value of this operator is actually negative. And that violated our assumptions. That means that all these off-diagonal elements have to be 0. And so that's equivalent to the statement that O annihilates the vacuum. Yeah.
It seems pretty specific. Maybe you mentioned this caveat, but it seems pretty specific to finite dimensional Hilbert spaces. Does it generalize well to dimensional?
It doesn't need to be, no. I picked any 2 states. The Hilbert space could be infinite dimensional, but I'm matrix in these 2 states, and then it's already a problem. Yeah.
I think that statement fails when A is also 0. In that case, O can map 0 to 1.
Yeah, the operator. Okay, sorry. You're saying if I set A to 0, then aren't the eigenvalues plus minus B? So I think it still doesn't work.
Oh.
Yeah.
Should it be B and B star? Just
Positive by assumption.
Yeah, it's a Hermitian operator. Yeah. Any questions? Okay, so yes.
I have a question. I mean, that this property implies that the O is actually some kind of, well, in some sense global, because it's localized into some kind of causal diamond. I mean, and then, I mean, shouldn't you say that the vacuum is the separating state for this?
Indeed, that's property 2. Okay, so property 2 is that, so we said any positive operator must annihilate the vacuum, and property 2 must not live in any finite space-time region. And property 1 implies property 2 because any operator that you can't have local operators that annihilate the vacuum. I could prove that, or we could just accept that. Sorry, is it another comment?
Yeah, but I mean, if I just take some kind of, if I just smear some local operators within some causal diamond and just take
Because if you square an operator, so the question is, why can't you just square an operator and get something positive? And the answer is that if you square an operator, then typically, let's say it was some free fields or something. If you take a field and you square it, then you get singularities. So you have to normal order, you have to subtract the singularities, and that can spoil positivity.
Yeah, but I think if I take some kind of local algebra corresponding to some cosodiamond, I can always do some like smearing and take bounded function to get some bounded operator which is well defined, and I think I can always square that.
No, you can't. You can't. You'll always either make something you'll always either make it negative or make it ill-defined. This is we could prove it. So we already proved that it has to annihilate the vacuum. And maybe I can quickly prove this one too. So the key ingredient here is Riesch-Leider. So what Riesch-Leider says is that you can make, so what Riesch-Leider says is that you can pick a region, say region U, and then you can act with local operators in region U, and that you can make any state in the Hilbert space that way. Not quite. It says that you can make a set of states that are dense in Hilbert space by acting in any open region U. So this is probably sort of heard it, because in particular I can act with local operators in region U stuff over there. Like you can make states that have stuff over here. But this is a fact about relativistic quantum field theory. You could think of it as, so the simple argument for this is that you can always do a series expansion. So like if you have an operator over here, O of x, you could just do a series expansion of that operator around this point over there. And so you can represent stuff that's outside the region in terms of stuff that's inside the region. That argument has flaws, so don't try to catch me on that one. But there's a theorem that you can always make any state this way. And now if we take if we look back at our positive operator, so let's act with our positive operator O on some state psi. Now what Riesch-Leider tells us is that we can take our state psi and represent it as living as an operator in U. So this is O, some operator psi U on vacuum. But now if O lives in some finite region, I can take psi to live in the complementary region. These two operators commute. So this is psi U O on 0. I just choose my Riesch-Leider region as somewhere that's away from my operator that has finite support. And now O annihilates the vacuum, and I just got 0. Okay. So the conclusion is that a positive operator with compact support is actually 0. In other words, positive operators that are not 0 or non-negative operators that are not 0 have to be infinite in extent. So that brings us to the ANEC, that the expectation value of this operator is non-negative. So in particular, this is integrated over infinite null ray, and you can't confine that to any finite region of space-time. That's important that you really do the integral from -infinity to infinity. So that satisfies one of the properties that we needed. The other property, well, that one's not obvious that that this operator annihilates the vacuum, but since we can prove the ANEC, it also follows that this operator does, in fact, annihilate the vacuum. So where did this ANEC come from? Is there a question? Yeah.
Yeah, I was gonna ask, like, in this ANEC, like, you wrote it for this light ray.
Yeah.
Does it work in general for like a geodesic going to infinity that has some signature, or like basically?
Yeah, good. So the question is, do I need to use a light ray, or can I use some other geodesic, maybe a time-like geodesic or something? And the answer is that there's no simple formula like this. There's no simple expression like this that's positive on time-like geodesics in general. I believe there's some proposals for things that are usually positive and mostly positive, where you integrate over a time-like geodesic weighted by something. But the nice one is only the one integrated over a null ray. Yes?
What if like singularities and like the null field is not complete?
So we're just in quantum field theory here. I'll come back to gravity in 1 second, but we're just in quantum field theory and Minkowski spacetime here. So there's no singularities. Yes?
I feel like we prove something stronger than just it can't live in a finite region. It has to support almost like an entire Cauchy slice.
It has to.
It can't be space-like to any finite region.
I think that's the same, isn't it?
I was just imagining like a Rindler wedge, right? Like it had support.
Oh, I see. Yeah, that's true. Okay, so the comment is that we actually prove something stronger, that it can't be space-like separated from anywhere.
Yeah.
So for example, you can't have a positive operator in the right Rindler wedge. I think that's correct, yeah.
But is that satisfied by a null ray? That's not satisfied by a null ray, is it? Is the null ray space-like to something?
No, okay, so the question is a null ray space-like to anything? No, a null ray is not space-like to anything, except possibly, we have to be very careful about this, other null rays on the same transverse plane. There things get iffy. Are those space-like separated or time-like separated? That depends on how you think about the points at infinity. Things get complicated. Okay, so where did this come from? Some history here. Actually, the ANEC first came from GR. Not derived from GR, but in general relativity, you want to impose energy. If you want to prove things in GR, in classical GR, you want to prove that no time machines, or you want to prove that there are singularities in a black hole, prove cosmological singularity theorems, area theorem, all that kind of stuff that people prove in classical GR, people were studying extensively in the 70s and 80s. Most of those statements require energy conditions. So you have to assume something about the stress energy tensor that your metric couples to. So a lot of the way you see those theorems stated, they assume a local energy condition. Like they assume that T00 is positive or something like that. Or that they might assume the null energy condition, which is that TUU is locally non-negative. But all those assumptions that go into those terms in GR, they're all false in quantum field theory, because we know that in quantum field theory, there is no local operator that's bounded from below. So this was sort of a puzzle and a loophole in the theorems that people had at GR, like no closed time-like curves, et cetera. And so the relativists began looking for a better assumption that was actually true in quantum field theory. And they did that by smearing the stress tensor. This theorem about it having infinite extent, this theorem goes way back to the 70s, so they were aware of this. They started smearing the stress tensor and looking for kind of the minimal smearing that they could do, where you would get a positive operator, and then they wanted to understand, okay, which of our results in general relativity still hold. And they sort of settled on the average null energy condition as the minimal thing that you could do that, first of all, seemed to be true. There were no counterexamples to the average null energy condition. And second of all, was sufficient for proving a lot of the things that you need in GR, like focusing area theorem. A lot of the proofs of those theorems can be relaxed to assume only the average null energy condition or a slight variant of it that I'll tell you about in a minute, instead of a local null energy condition. You can check pretty easily that the ANEC is true in free theory. So the proof of that goes like this. Integral du TUU. Let's do a free scalar, let's say. So in a free scalar, this is integral du of du phi squared. Now, we're not done. That looks like it's manifestly positive, but we're not done because this is an operator. And when you multiply two operators together to make a composite operator, you need to normal order. So it's not immediately obvious that this is going to be positive. And we know from the discussion just now that if I didn't do the integral, then normal ordering would spoil positivity. So normal ordering is really important here. But you can take the expression for the free field, plug in your A's and A daggers and E to the I kx's and all that, and do the integral du just very explicitly in free field theory, and you find that this is a squared operator, a well-defined squared operator without any normal ordering outside. So that gives you a proof of the ANEC in free scalar, and this was extended to various other examples back in the 80s and 90s. In interacting theories, it was also proved in the 90s for interacting two-dimensional conformal field theories. As far as interacting theories above 2 dimensions, the first derivation of this came from quantum information, monotonicity of relative entropy. So there's I won't go into one, you can ask me about it later, but there's a very close connection between these null energy operators that we've been talking about and the modular Hamiltonian of the vacuum state in the quantum field theory. And you can use quantum information inequalities like monotonicity of relative entropy to prove the ANEC in interacting field theories. This was done in 2016 by Tom Faulkner, Lee, Parakar, and Wang, I think is the paper. Then around the same time, a little bit later, there's another derivation using causality that uses some of the ingredients talked about, like Rindler positivity and analyticity and so on. And you can show, I'll talk about this more next time, but you could show that imposing those ingredients, that causality of 4-point functions requires the ANEC to hold as well. It's a question, yes?
Just to make sure, psi is the state on constant V slice?
Psi is any state.
Yeah, is the state on the slice with a constant V, right?
I'm not sure, so.
Because you integrate over U, is it the constant V? Or?
No, okay, so the question is, where is the state psi? Is it on constant U? No, psi, once you have a state in quantum field theory, you don't have to say where it is. The state is the state. So this could be a state defined on the t equals 0 slice. And then we can evaluate this operator as an expectation value. We can evaluate the expectation value of this operator in that state. By just think of this integral as involving a bunch of e to the IHTs in order to do the integral. But that evaluates the operator in a state that was defined on the t equals 0 slice.
The statement of ANEC is for all psi, right?
Correct. The statement of ANEC is for all psi. So yes.
Is there any condition you need to put to make sure sure that the integral really converges to a positive operator. The integral where you.
Yeah, so the question is whether there's conditions on the integral. The answer is that this is only positive on states where it's finite. You can make states in quantum field theory where energy, take like the uniform energy density state. That's a weird state with infinite energy, but the ANAC doesn't make any sense on that state. So the careful that it's positive whenever it makes sense. So we're talking here always about quantum field theory, not gravity, and quantum field theory in Minkowski space, not in some curved background. But I just want to make a couple remarks about what the situation is in the more general case, like if you take your theory and you put it in a curved background, or if you couple it to gravity. So first of all, in QFT in curved space, so in a fixed curved space, the ANAC does not hold. The average null energy condition is not true. There are counterexamples to the ANAC in curved space. Second of all, in QFT coupled to gravity, just perturbative perturbative gravity here, treating the graviton perturbatively, treating gravity perturbatively. The ordinary ANAC is not true. So the ANAC, as stated there, is not true because so there are counterexamples to that. Probably the most interesting one is Hawking radiation. So I'll just the ANAC implies that the area of a black hole always increases. So ANAC implies the focusing theorem in general relativity, and that implies that the area of a black hole always increases or never decreases. But when a black hole Hawking radiates, actually the area of the horizon goes down. So the ANAC has to be violated. And in fact, you can calculate the stress energy tensor on the horizon of an evaporating black hole, and you'll find null energy and violates the ANAC. However, the achronal ANAC is a modification of ANAC. This one is believed to be true in quantum field theory coupled to GR. So the achronal ANAC is the same statement. It's the same formula. It's the same formula, except you're only allowed to apply it on achronal null rays. So an achronal null ray is a null geodesic or achronal null geodesics. So an achronal null geodesic is a null geodesic that never enters into its own future light cone. So if you have, maybe it's easiest if I explain this by counterexample. So like if you have a black hole, there's a photon orbit around a black hole. Photons can go in a circular orbit. It's unstable, but it doesn't matter. So there's an unstable photon orbit around a black hole. If you think about what that's doing in space-time, the photon is kind of spiraling around the black hole world line in space-time. And that's chronal. That's chronal because you can take a time-like, you can connect 2 points on that world line by a time-like path. So in situations like that, the ANAC can be violated, but it's believed that the ANAC holds on achronal null geodesics where it's impossible to connect any 2 points by a time-like path. There's no counterexample to that, and I think it's probably true, but there's no proof. Yeah?
So achronal geodesics are just the boundaries of trap surfaces? Would that be correct?
The boundaries, so the, that's not necessarily true. It's true that null geodesics that lie on the boundaries of causal domains are always achronal. Yeah. Okay. Yeah.
What about this example that you said, like if I take a null geodesic like on the horizon of a black or an evaporating black hole, is that a chronal?
No, that's chronal.
Is that chronal?
That's chronal. Yeah. But it's chronal because the black hole is shrinking. If the black hole were not shrinking, so the question was whether in the evaporating black hole, how that gets around the achronal annex. The answer is that these null rays, where it's violated, are actually chronal.
Could you again clarify what QFT plus GR? Is it just spin 2 particles, or you have to put it on a top for like is it gravitons on Minkowski space? Does that?
No, it's not. So the question is, what do I mean by QFT plus GR? I mean like what we do like what we always do when we're not doing non-perturbative quantum gravity. So I mean, you can have fully back-reacted curvature, et cetera, but you're treating gravity as a quantum field theory in terms of the metric. Yeah.
Are there examples for non-trivially curved spacetimes where we don't have achronal, where the achronal annex holds?
Are there examples of non-trivial spacetimes where the achronal annex holds? Okay, so this gets into funny territory here. So one of the reasons that the achronal annex is believed to be true is that almost no spacetimes have achronal null rays. So there's another theorem that says any generic, if under some definition of generic spacetimes just don't have achronal null rays, so the achronal annex becomes vacuous in that case. The interesting cases are the ones where there are achronal null rays, like things that like vacuum or things that are near vacuum, and then you have a non-trivial test here. Yeah. Was there another?
Yeah, just to clarify that in particular, this doesn't fix the counterexamples you mentioned in curved spaces.
Good. The counterexamples. So the questions about these counterexamples. The counterexamples are not solutions of general relativity coupled to quantum field theory. They're things where you just impose by hand, I want this metric because I feel like it, and you put your quantum field theory there. The statement here is that if you have to solve the Einstein equations, and then when you solve the Einstein equations, the achronal annex is true in that background. Yes?
When you say generic spacetimes don't have chronal null rays, like how is the Schwarzschild?
No, they don't have achronal. Generic spacetimes don't have achronal null rays. Yeah. I might have said backwards, but that's what I meant. Okay. Yeah.
I'm a little confused. Like I thought you like generic spacetimes. It depends on what context, but I thought usually they would lead to black holes. So is it that like most black holes still don't have achronal rays,
Yeah, that's right. So the question is, what about black holes? Do they? Yeah. If you just have like a Schwarzschild black hole, then there are achronal null rays. I'd have to think about that one, but I'm not sure whether there are. But so generic means that generic means that any path you go on encounters some curvature. Roughly, like that's the intuition for the technical definition of generic. And in that type of generic spacetime, you don't get achronal null rays.
Got about 5 minutes.
Okay, so in the last 5 minutes, let's talk about energy correlators. So I want to consider an excited state created, for example, by a high energy collision we could consider any excited state, but the prototypical example is something like the quark gluon plasma that's created at RIC. Okay, so, or it could just be something you get by taking an operator and smearing it with some momentum and inserting it in vacuum. I'll give a careful definition of what I mean by this in a little bit. But for now, let's just draw a picture. Okay, so you have some localized high energy excitation of some stuff. And that stuff is flying off every which way in your experiment. The energy operator E of n hat, is the operator that measures, so imagine you're doing an actual experiment, you have a bunch of calorimeters set up around your experiment, and so you have a calorimeter at each unit vector on the 2-sphere, that's n hat, and the energy operator measures the total amount of energy deposited in your calorimeter labeled by n hat. So we can write this as a limit at r goes to infinity of r squared, integral from 0 to infinity dt, ni t ti of t r n hat. So I've just calculated the energy flux into this calorimeter cell and taken the calorimeter cells to be very far away. When we do that, we have to reweight by the size of the calorimeter. That's this r squared, and so we get something finite by taking this limit. If we draw a picture of what's happening in Minkowski space here, I'm going to draw Minkowski as a diamond, where these are our u and v directions, but this is a conformal diagram where I've squashed in infinity. So we have scry plus up here, scry minus down there. Then the way you should think about this is that your experiment happened here. So that's where your blob that's where your quark gluon plasma was, or whatever. And then the constituents zoom out at or near the speed of light towards infinity. And then we have our calorimeter cell. Here's our calorimeter cell at some fixed distance r from the experiment. But when we take r to infinity, like we did in that limit over there, then we can just think about this calorimeter cell as living on scry plus. And if we choose our usual null coordinates, u, v, and x, with v hat minus u hat, that's the spatial direction corresponding to where our calorimeter is situated, then this energy operator is the same as the limit v goes to infinity of v squared integral du tuu minus infinity to infinity of u v 0. So energy operators that measure this very physical thing of how much energy you get in your calorimeter in an experiment are a special case of the average null energy operator, where you take that operator and you put it up on scry plus. Okay. So energy operator is just the NX operator up on scry plus. And these operators are important for experiment, things like RIC. They measure the energy one-point function. That's just literally the energy measured or deposited in the calorimeter. They also measure energy correlators, things like E of n1 hat, E of n2 hat, etc. You can insert more of these energy operators. And again, these are very physical quantities that you can extract from the data from your experiment, because you just take all your data coming out of your calorimeter cells and you calculate correlations of the energy deposited at different angles in your experiment. And so this is a very rich set of observables that you can think about that are especially important in things like QCD. In the last few years, well, these have been studied for a very long time, but especially in the last few years, the program of using these type of energy correlators to probe the physics of QCD has been revived and really come back to life. And in fact, the energy there's a three-point energy correlator. The three-point energy correlator is currently one of the, well, it's been used by the CMS collaboration and is the best measurement they have of strong coming from jet substructure in their experiment. So you should, in the context of actual experiment, you should think of this as happening somewhere inside a jet. We have all these QCD particles coming out, and you're looking at correlations of what's happening inside that jet, and you can use that to compare between theory and experiment, and brings this whole technology into that. Good, so I'm not gonna be using it for that, but I wanted to introduce it that way, and then we're gonna use these energy correlators for our theoretical purposes, yeah.
So in actual experiments, I would assume they integrate over the whole null array. So is there like a natural notion of cutoff that you choose?
Yeah, so the question is that you can't integrate to infinity in experiments, so what do you do? If you want a literally positive operator, you have to integrate to infinity. But of course, in experiment, we never go to infinity. We still measure positive energies. Basically, as long as you turn on your experiment at some finite time and then turn it off at some finite time, maybe wait a few milliseconds after you turn it off, then these energy operators are still positive. Yes?
I saw more questions, but we're already over time, so let me ask us. Let's hold them to the break. Let's thank Tom for his lecture.
I just wanted to mention, as many of you know, the T-shirts are here. Are Sanjay and Lisa here? Do you want to just come up for a second?
Sanjay was here early.
So here it is. So I know all of you put this together, voted on it. Sanjay and Lisa ran it. Nice job, everybody. Thank you all.
Thanks to Junwei for the design for the back, and Anirudh and Aiden for the design for the front. So thanks to them. They're the ones who made it happen. Yeah. Also, stickers arriving tomorrow. So
Pay me, because I paid out of my pocket.
So if your design didn't win, but you still want something to remember your design by and something else to remember Tassi by, they're stickers. So, hey, Lisa.
Thanks, everybody. So Mara is right there with the shirts. If you didn't get yours already, you can go grab it now.